scattering is a transformer for image classification task. Basically, we develop a transformer for recent tasks. Like also you know already transformers are there for the natural language processing task. So we develop transformer for visual task, rate, image classification, object detection, digital segmentation, all kind of visual tasks. As soon as we did a downstream task like time series, we extended that to time series tasks as well. So today I will discuss about scattering is a transformer. So this is basically is a spectral transformer. How it make efficient as compared to the recent transformer that is there in original recent transformer from Google. Google in 2020 is the first presented a result transformer known as AI. So in that they have a they just inspire an NLP task. Yeah. Today says that we discuss about the more and related work and business cases, which and business cases. So the task is like given an image, the model we can classify into the top 5 classes. Like you can give it any kind of image and you want to classify, you want to, classify this is a cat, this is a dog, and any other category you want to classify, that this transformer can help to do that. So basically, previously people are using for the convolutional neural network to doing that. So the convolutional neural network has a problem with the accuracy and the model is a huge model. So they inspire technology, the transformer technology, and they try to do it. So our objective is to make more efficient. Efficient means what any practice and in terms of number of parameters, like if you have a number of parameters are more, so it retains and more memory when you do the inference in that the latency, how much cost you are paying while you are doing the inference. Like you have trained your model, then you will do the inferencing and identify task when what is the throughput is present and latency, throughput, all this inference, the cost with the economic. The third one is how much computational cost is required, like during resources cost staying on. So it should have a more complicated like transformer, it requires a huge number of computational costs that are discussed. So if you have that, so you need that old skill and curricular. So we did we develop a transformer which can go the better, is less number of parameters and less computational cost and better inferencing time. So all of you know about this transformer attention, or you need in the today era in large language model, the backbone of relevance of the transformers. So all kinds of large language modeling, the starting from GPT, Chat GPT, GPT-4, Turbo, then Mistral, then Llama 3. Recently, Llama 3 is they put in for Llama 3, then 5P. All this modern backbone is transformer. If you make efficient in transformer, all these elements will also work in that case. But there are, so what is this transformer? I will not go detail for mathematics. So basically, they have an encoded block. There is this is the encoder and this is the decoder part. So encoder block. So there is two parts. One is multi-headed self-attention, and then there is 0.4 on neural network is there. So they what it is multi-headed self-attention. So what it will do, it will do to give the key query value to word about it. So this will multiply, these two will multiply, then pass the value in there to get a attention added. This scale dot product is further classified. This makes a cost of matrix multiplication of orders and scale. Let's say we'll have a sentence, let's say what's your name, and you have to generate the answer for that. So the sentence, how much big your sentence, the square of that is the cost for this multiplication. So if your sentence is right now, it is a 10 words, like now we got 20, 100, 1K, maximum is 32K. Like how many is one par in the two paragraph one document here. Let's say when you go for the genome sequence, so you have a millions of tokens are there. So at that time, so 1 million square is there. So think about 12. That is a huge cost. Not only the parameter, it's a computational cost and latency also increase in that case. So how will you reduce this multiplication? If you have any other technique to replace this one, so this is a Orange n square. If you know that, so on the computational cost is measured in terms of folds n square. This is of n squared task this time. So how do you reduce this complexity? So this is what our research is that, and uh, all this thing, whatever I'm discussed is published in July 2023. December, this work is published. So the main problem of transformer is the computational complexity. So it increases quadratic with sequence length. As I discussed, if my sequence length is increasing, so my computational complexity is going that increase it increase. So it is okay when I'll have the like a 512 or a 1K sequence length is there. When if you ask for the document or if you have a complete thing, yes, right now LLMs are used for the creative summarization. So that case, the computational cost is going high. So let's say when you have a complete thing, yes, it's the like more than 1 million tokens are there at that time. This increases the complexity, increases the quadratic thing at 8 to 112. It's a very huge cost. Just the memory is it's about the reshaping work is a very most transformer. When in 2020, Google is published a model known as vision transformer that is a huge memory. It's like real-time memory with Alzheimer's. It's like 500 MBs for transformer. It has been before 76 something like that. So how you reduce that number parameter? And the second one is computational cost, like number of the SIM flows. The floating point operation, when you have like you got the 32-bit mixed precision, 32-bit precision. And recently Microsoft has published like 1.5 gig LLMs. So you won't require in 32-bit, you require just 1.5-bit LLM is enough for those that. So like that, this will boom that you will reduce the number of the flop. The Z flop is a gigaflop. How many gigaflops is required? The latency is more important to the business purpose, like inference. Let's say you type some question, how much time will you need to wait it? Up just 1 second and 2 seconds, that's how they achieve. Latency time is more than nobody will purchase my card. So also this in case of the recent task, these customers are not able to give a fine-grained information. Fine-grained is information and like the low frequency information, the person's low frequency information is the same of a person. Where the fine-grained information is the units and all that I know careers and position of eye, all this information is linked to the transcom. So to do that, the main cost is quadratic sequence length. How we should reduce that? In now, all these LLMs, they are also having a quadratic cost. So last December, one paper is getting as Mamba. Mamba is a state space model. It's compute all this token in a simultaneously, no need for quadratic complexity, it's a linear complexity. So the Mamba, this is the first paper what uses the linear complexity. Mamba is a state space model. It's a recent research. People are working on a state space model. Different state space model is the alternative for the transform. So what you are using for another like transformers are the backward models. Now you can replace those backward models with state space models. There are n number of state space models. Just like put a Mamba and Simba. Simba is basically for the vision and time series. Mamba is for the language modeling task. So you can start with S4, the structural sequence state space model, S5, then GSS, lots more are there. So within the 4 months, there are like it can vary with around 500 papers. Then papers are there in our archive when the state space model and how you them. It to transformers complexity and they tested on a huge sequence like 1 million tokens, then genomic sequence, then DNA sequence. They are testing that and it's successful. And the complexity is the order of L. It's instead of N instead of N square, whatever there in the transformer. Then this is where latest work, whatever we found this study, the SCT. So there is instead of N square, you can try with the spectral model. What our method is the spectral model. Instead of N square, you can go for N log N. So it is less than N squared. So you can go for the N Fourier transform you reward in class 2 and intermediate. The Fourier transform with the spectral model is convert the time domain to the frequency domain. All this frequency domain operation is depend upon the global and capture the global information and the complexity is analog. So when you have a median of token, at that time, this complexity will snap in it. So, and based upon that, we recurrence type and gigaflops answer icon. So, today we discuss, just to give a glimpse about Simba and discuss the SCT transform. Right. So, this is what the recent research direction Simba is an alternative for transformer, and this is for sequence modeling task. Starting from self-attention, spectral mixing, Hamilton mixing, lambda, into all kind of networks are ready in the stream space model. And this is basically for the channel mixing. This is all about the architectural view. You apply a layer none, then a sequential, the secret mixing network, then the channel mixing, then a residual connection and there is three variant of channel mixing that is inactive, MLP, and M2 is the monads mixer kind of things. So these are making more efficient way of channel mixing. What is channel mixing? What is token mixing? Channeling is the feature direction. And the token is like what is your name? What is interact with your interact with name. That is what known as the sequence mixing, token mixing, all are synonyms. Channel mixing is related to feature. How many features are there? Let's say in a word, what are the different features for a particular word? You can find it. Let's say this person, features are the legs and position of eye, position of nose, then golden ratio. All these things have one features are like that. Like that, it is for each word, there are n number of features they will find, and based upon that, they will mix it, and they will find an interaction with each other. So, the Simba uses MAPA is a big one for the sequence mixing and in FMT, the Einstein Fourier transform, fast Fourier transform for channel mixing. And these things are there, means no need to go there, it is already there in this paper that is simplified MAPA architecture for reason and times multivariate times. Any kind of type series and RNB task, it is more effective. So it is basically a very simple network. There is a linear projection, then conditional layer, then a gating network. This is what the state space model for the for timing. I'm not discussing state space model. The state space model basically it's a linear dynamic system in which you know the string mass system. So how many F equal to Mn, force equal to mass into acceleration, how you are calculating in a string mass. Similarly, they calculated the model it in SSR, and this makes a more efficient way of computing sequence modeling tasks. Right? Then they have the Einstein effective. Einstein effective basically use the Einstein matrix multiplication in the first Fourier domain. In the first Fourier domain, just you have a Einstein matrix multiplication, and that gives them a better performance added. So this paper is available and recently March So you can check it. So another way of doing that is the spectral wave. It's a very easy and effective way to do the spectral transform. You use the spectral transform technique that for the sequence mixing. So there are different spectral transforms out there. Like I discussed the fast Fourier transform. Fourier is basic. Wavelet transform, Fourier transform. Then you have a scattering transform. Dual tree complex wavelet transform is another transform. The cosine transform, sine transform. And all this transform makes matter in terms of mixing sequences. I might walk into that another go. So what scattering transform is uses a basically backbone is a DTC developed duality complex wireless transform. This code is available. You can check it. That. Then they use a tensor blending method and an Einstein blending method. Finally, they use a Tenormans and the Tokyo. Yeah. So the contribution wise, they use a scattering vision transform for image class. It's a counter for everyone. Then they will use this architecture, the low frequency component. I have discussed something like the fine-tuning information and the work probably the coarser and the finer information. The low frequency basically give the structure of the object, where the high frequency information gives a fine-grained information of the object. So this platform takes us to study the low frequency and the high frequency component and try to give it. Finally, they use the Einstein matrix multiplication both in general direction and the token direction to get the better performance. So they have compared with recent transformer networks like Fourier, Foreman, WAD, other thing. Here you can see SBT. This one is better. Means accuracy, top one accuracy versus the number of slots. You can see SBT is much better as compared to the other tools. So it's more close towards the accuracy is much higher. Similarly, when you see the number of the flops, G flop, the SBT is much better as compared to this one. This is for the hierarchical models for the vanilla architecture. The co-architecture one is the vanilla architecture and hierarchical. Whatever I have shown is a vanilla architecture. So this is what the recent transform now proposed by the Google. That is the 16 cross 16 words matter in that. So they divided images into the patches, like if you have any kind of image, just you crop it in a 3 cross 3 or 4 cross 4 or 16 cross 16 what Google has did. Then the user just find the embedding that in the image space to the embedding space. So these patches are converted to the embedding space. Then they added a position encoding. Since an image position is matter, like this should be in position 1, this things will say. So they embedded all this position, then passed to a transformer encoder. The encoder to whatever the transformer is there. This encoder, this is what the encoder in other classification does. Right? In order to be more common. That but just the classifier I done in, and finally they classify into the class, ball, the balls and all everything. So the encoder of the transformer is similar to the natural language processing, multi-layered self-attention, and then the multi-layered perceptron and a reciprocal case. And as I discussed, the problems to this transformer has because the complexity, memory size, large number of parameters, and also it's not able to capture the fine grain and so on so on. Like the shape of a just a give a shape of a person. Okay, it's like a car. The shape of object is like that. So you can classify as a car. But different variant of cars is not able to distinguish. So the vision transformer face this type of problem. So the fine grain classification, when you have a the fight when object class in design, like if you design kinds of type learning, different types of shirt, different types of fact, or a different unequal words category, one fighting the class design is spam from a modern phrase about it along with the So we saw that there are another paper in News 21 years the top most conference in AI and ML domain. No. So they just classify a high frequency and the low frequency in a patterns and domain. The problem in this high frequency domain is still they are using evidence like aqua. So they are able to capture or fine grained information, but way to have a computational complexity. They are the same computational complexity and like orders and since they are using KQV, the attention mechanism. So how will you solve this one? So to solve that one, as a paper is stated as ZFNet. ZFNet then use a global center network, the fast Fourier transform to build a thing. Then they use a MNP layer and this. But what's the problem with that? So they are not able to capture its in-bed information. So the previous model, they able to capture a fine-grained information, but they have a skill complexity, otherwise square. Here the complexity is solved, but they are not able to capture a fine-grained sensor. Since the nature of the fast Fourier transform, they convert the time domain to the frequency domain, the spatial domain to the sequence domain, not able to capture segregate both frequency component as high frequency component. So another matter is that 12 VAT, this is in 2022, it's ordered in December. So they convert time spatial domain to the frequency domain using bed-like transform, but still they are having the much here than self-actance and then this paper is basically in a frequency domain. So what our technology we used the scattering transform is convert a spatial domain to the frequency domain. Then we use a low frequency component and the high frequency component. First, this transform reduces the complexity of any spectrum and login. The second part, it can able to segregate the low frequency and the high frequency component. Then the third part is like how will you reduce the gene curves and all. So that is what the types of blending method and Einstein blendingness. Einstein blending method is the Einstein matrix multiplication and Quincy-Knows is basically kind of matrix multiplication could reduce just it's multiply this that CD cross CD instead of complete multiplication, just it required this time computational non-density. So X plus W plus CD plus statement, that is what the computational cost is, right? Instead of that, the Einstein netting method is just CD plus CD in just CD. So it's a very small number of computational costs that keep it out as compared to rest of the transformer. That's why we used Einstein netting method in case of high frequency. Since high frequency, how will you capture high frequency component? Like it's each an infinite angle. If you apply the transform, then you will capture the high frequency component. All this angle, the rotation invariant, the scaling variant property. So to do that, so you have a constant blending method to capture that one. So why there are the 6 components, like we use for the 6 component, you can use total 360 degrees there. We use for the 15 degrees, 45 degree, 135 degree, like that. We use that can be increased to 36. That can be increased to 313, 316, or kind. If you want the inside dealing, if you want more finding, that can be also possible. That we use a weighting method. So how much, so what are the frequency component we need to pass through the next layer? That can be decided by this weighting mechanism. So this is the gaming mechanism we use to learn how much frequency we pass to the next layer. Then we combine these two, it will inverse transform, then pass through it multi-layer percentage. This is what basically the core part of our model. So us in the second contribution, we will use scattering layer in the initial layers and the potential layer in the final layers. Why? Because the initial layers, as the study and research, that initial layers are able to capture lines and edges and images. So in any image, if you want to have a first layer, you decide lines and edges of a face and the object. If you have a second layer, and then second and third layer of must able to try to have a contour of an image, and fourth and sixth layer or that you give an object level information. Since the frequency domain information are very good in an initial layer, means they are very good to capture the nice edges. So we use this spectral layers, that is what it's scattering layer in an initial layer. So the final layers are the attention layers. So recently, Google uses similar kind of paper known as the Grissom. Grissom uses the same technique. They combine the attention as well as the state-space model. Means the state-space model, only of the model is characterized by the synchronization of filters. That is the first Fourier transform. So this is what the vanilla architecture, and this is what the hierarchical architecture. So in case of the image, you can see the hierarchical properties that let's just take if you want in the stage one, the first layer, you have a bigger size image and patches as the layers increases to decrease the patch size. That is a more efficient way of doing that. So initially in VBT, the periodical vision transformer proposed that we also use a similar kind of technique to do that. So, or this is what I have discussed. In picture, and you can see the tensor black methods. You require this much size of a vein, and if you just element-wise multiplication instead, so you will get this. In case of Einstein blending method, you will require this much number of parameter. Only this much multiplication is there to get a complete information. So within a very small size network, weight parameter instead of the complete weight parameter, we get similar or better performance than tensor blending method. So we have a complete architectural diagram how this how it getting the mechanism are, what is that the representation embedding, how many attention heads are there, all these information are present here. The data, we first train our model with the ImageNet and so use data. ImageNet it's 1.2 million data for the training data from validation data when is a 50K data on that. Then whatever our train model that we predict for that downstream task, like in a different data set like C for 10, C for 100, and Stanford car is our data set to get to check that all the transpose attendees documents. Then also use for downstream tasks like object detection and MS Coco data sets. So this I have discussed the modern performance for the vanilla architecture. This is for the number of the parameter. This parameter is very less. You can see that SVT is written a very small size. It gives a better performance as compared to the other one. This table will give as well. You can see it has SVT for a small size network, just a 22 million parameter. It gives a performance of 84. Where you can see it has a number of forms like 3.9, and it gives a top one accuracy. Top one accuracy means the correct class to be present at the first instant. Or if we take a top 5, the correct class would be present in top 5. That is known as the outside vectors. So similarly, in case of the where size of the last model, it's a much better. You can check in the paper. So within a very less parameter, it is 85.7 and the year is 85.2. So the equivalent is around the 1% on the state apart contents. This is what the state apart all the transformers in the literature present both during starting from calculation memory network when the MFP mixer, spectral network, all kinds of network. The second thing we discussed about different kind of spectral network, comparing the different kind of spectral and how this performing. So you can see SPP need for the vanilla architecture it's 80 as compared to GFNet. GFNet, as I have shown that the Fourier transform this method, and also FNet is a Fourier transformer of this method, which being used, it was hard Fourier transform. Similarly, the hierarchical, we talked about the isomer and LIT A2, when LIT V2s are sold that the segregated, but in attention domain. So, for the top one performance, top one is 85.7 for the SVT. And so right now it is a state of our model for the image classification, image segmentation task. So for the backmap, so how use low frequencies, high frequency in a channel mixing and broken mixing? We see that in a low frequency component, we induce the tensor mixing for high frequency component to use the Einstein mixonomic. So that's the reason it gives a better performance as compared to the rest of that. This is more example. Different kind of spectral, like this is a Fourier convolutional, this is a Fourier network, this is Fourier neural operator. So basically this kind of operators are easy for weather forecasting and 7 days weather forecasting. So they perform with Fourier neural operator. Then the wavelet gating network and SDT. SDT seems a better performance as compared to rest of the ends. Then, as I discussed, the transcode learning task, so being put model with Rayman and just web, and we started given and see for 10 datasets, so it's an state of art or any see for 10 flowers are in dataset. So you can use any kind of listening data set or a decent task. You can take a Bacon model, SPT, and fine tune an So just give it required fine tuning cost instead of turning from the stacks and the that and all. So it's kind of an adapter. If you use the adapter technique and SPT, that will be like that everything is that. Then this is for the task learning. So we learn the image classification task, but if you want to do that image segmentation or express segmentation task, so how it is performing, that we show that it is better than the PBT and the LIT V2. Then since it's a filter domain, sequence domain, we show the characterization of a filter, how this the low frequency component. It will in just the structural information. You can see this structural information. For the high frequency orientation one, it will give this direction with 35-degree or a 45-degree orientation. And this is the another kind of orientation. So, or you can see this is 135-degree orientations are there. So there are 6 orientations just clear for the 2 orientation here. So here you can see that 35, 75, 135, all kinds of orientation, all 6 types of orientation is captured using this filter characterization. Yeah, business cases you can use for any other than backbone else spectral scattering Mason transform you can use, and also you can use to reduce the computational complexity in plotting, that is number of the parameter and inference time. That in that case you can use. So you can use peaks and analytics